Welcome to Lesson 2, Compare and Analyze Moving Costs. Our objectives are to compare the hourly costs of moving companies in order to make some financial decisions. We are going to need to use a system of equations in order to solve these types of problems. Here is a chart that shows you the average relocation costs in the United States. If you notice, if you're a homeowner and you're relocating, it will cost about $90,000 to move the contents of your home to a new location. And perhaps the reason that this is higher than if you're a new hire is because if you're a current employee, oftentimes your company will pick up most of this tab. So you let your movers pack your stuff, load it onto the truck, drive it to your new home, unload it, and unpack it. So you are bearing the full brunt of what they cost. Whereas maybe if you're a new hire, you don't have them do quite as much, depending upon how much your employer is willing to pay. If you live in an apartment, so you're a renter, look at how much cheaper it is. And most of the time, that's probably because you have less goods, right? You have less furniture, you don't have as many things in an apartment as you would in a house. But still, the point is it's very expensive to move, and the more you know about moving and the cost of moving, the better equipped you'll be to make some decisions. So let's look at our example. In this example, you are being relocated to Fort Collins. You have two options. You can move on a weekday or you can move on a weekend. So if you move on a weekday, you're going to be working, your friends are going to be working, so you're going to need the movers to do more. So they're going to take more hours because they're going to be packing and unpacking your stuff, loading and unloading your stuff, and they quote you down here as a total of $720 to do that. And they'll give you some estimates on hours based on what you tell them as far as how much stuff you have. On the other hand, if you move on a weekend, you may get your friends to help you because they won't be at work, and so it may be a little bit cheaper. So you're hoping that you can really cut down on this packing and unpacking part because your friends will pitch in. But you know, the loading and unloading, you're probably still going to need a lot of mover time to do that. So your movers have quoted you $400 if you do a weekend move with these approximate hours. So your goal is to determine, though, the hourly cost for loading and unloading as well as packing and unpacking so that you can make some decisions about how you want to spend your time. So there's a few ways that we can solve this. We can solve this by graphing, or we can solve this using algebra. And we're going to actually do both, but first we're going to graph. In order to graph, we have to set up two equations, a system of two equations. And before we set up equations, we need to identify the variables that we're using. Well, typically we use x and y, those are the most common. And so let's just say that x represents the hourly cost for loading and unloading, whereas y is going to represent the hourly cost for packing and unpacking. And I can set that up. You can reverse this as long as you identify your variables. So the next step is to write your equations here. So this is step 1. Right here, put 1 by this. And then step 2 is to actually write your equations using x and y and this data up here. So I know that it's going to take 6 hours times however much it costs to load plus 5 hours times however much it costs to pack, basically, for a total of $720. On a weekend, it's going to be 4 hours to load times however much it costs per hour, plus 2 hours to pack times however much it costs per hour for a total of $400. So in order to graph this, the best thing to do is to write it in slope-intercept form. So I'm going to go through just one of these to give you an example and to remind you in case you've forgotten. So step 3 is we need to actually write this equation in a graphable form, slope-intercept. So here we have our 6x plus 5y equals 720. So if you remember slope-intercept form is y equals mx plus b. b is your y-intercept and m is your slope. If we can write it like this, it's very easy to graph. So I need to move everything away from the y, so I'm going to subtract 6x to the other side, which will leave me with 5y on this left side. And then on the right side, I have this at minus 6x plus 720. My final step then would be to divide all my terms by 5. So I would divide the negative 6 by 5 and the 720 by 5. And I would get my final answer. So my final answer is going to be y equals, my slope will be negative 6 over 5x plus 720 divided by 5 is 144. And this is the same equation that we started with, it's just now in slope-intercept form. And that's what we would do for the second equation as well. So let's go ahead and graph our equations and see what happens. Okay, here are some graphs, or a graph of our systems of equations, and we have graphed both. You can see this first one that we switched that has a y-intercept of 144, and that's here, and you can see that right here. That's 144. Now our slope is rise over run, remember, so we go down 6 over 5, down 6 over 5. But if you'll notice, our scale is pretty large in order to fit this 144 and the 200 on the other one. So probably the best thing to do is to switch the negative 6 over 5 to negative 60 over 50. So we multiply both the numerator and the denominator by 10. And that way it doesn't change our slope, but it's a little bit easier to go down 60 over 50. Okay, so we have graphed both of these. Here's our second one, this 200 right here. And we've gone down, and we could do the same thing here. This is negative 2 over 1, which is the same thing as negative 20 over 10. So we've gone down 20 over 10, and we've graphed. Now what we've done here is we've highlighted the interception point, and this is going to tell us what we need to know. But what I'm missing from this graph are some labels. So what did we define x as, and what did we define y as? So we should go back and double check. Here we said x was the cost for the loading, unloading, and y was the cost for packing, unpacking. So I'm going to put a label on my graph under x that says loading. So this is our loading. I'm just going to say load. And our y was our packing, unpacking, and I'm just going to say pack. Okay, so then that can help us define what this is. So 70 represents the cost, that's our x, to load. So 70 is load, put an L here, and 60 is the cost of packing. So it was $60 per hour to pack and $70 per hour to load. This is good information to know because I know that now it is more expensive for the movers to load and unload the goods than it is for them to pack. So if I could get my friends to come over just to help with the loading, then I can maybe really cut down on the loading hours and save myself some money. Okay, oftentimes when we graph, especially if we're graphing by hand, this intersection point may not be that accurate, especially if it's $70.25 or something like that. So we always want to verify our work algebraically, and for some of you it might be easier to come to this solution by using the algebraic methods of solving a system. So what I'm going to show you today is solving using elimination, since these problems are really set up more for elimination than they are for substitution. So the way we do elimination, remember, is that you have these two equations, and it's just like the term says, elimination. We want to eliminate one of our variables. So our goal then is to add these two equations together. In other words, add the left side of this other equation to the left side of our first equation, and then add the right side to the right side. They should still be equal. But when we add these together, our hope is that either the x's zero out or the y's zero out. Right now that doesn't happen because we get 10x and we get 7x. So oftentimes what we do then is we multiply these equations by some number in order to change the coefficient of a variable. So let's go ahead and go with the y's. Let's eliminate the y's. And if I look at the y's, I'm seeing that if I can turn these into 10, one positive, one negative, they can eliminate. So all I have to do is multiply this top equation maybe by negative 2 to turn that into a negative 10. Which means I would just need to multiply the bottom equation by 5. And then I will have brand new equations. So I'm going to go ahead and do that. So negative 2 times 6x is negative 12x. Negative 2 times 5 is negative 10y. And then negative 720 times 2 is going to be negative 1440. Okay, and now I'll do the same thing with the bottom equation. I'm going to get 20x plus 10y, which is what I want, one positive, one negative, equals 2000. So now I'm ready to add these two equations together. Negative 12x plus 20x is 8x. As I said, these are now gone, which is what I wanted. And then if I add these together, I'm going to get a positive 560. Finally, all I need to do now is divide everything by 8 to figure out my x. And my x, remember, if you look back, was loading and unloading. So 560 divided by 8, well, 8 goes into 56 7 times and into 0, 0. So that's $70 for loading. And then if I wanted to figure out, and that's right on with what we got before, but now if I wanted to figure out my packing and unpacking this way, I would just need to take and plug in the $70 for x in one of my equations. And I'm going to use that bottom equation because it's a little bit smaller. So I would take 4 and plug in the 70, replace the x with 70, plus 2y equals 400. And then I would go ahead and solve. So I'm going to simplify first. Subtract 280 to the other side. And I'm left with 2y, this is gone, is equal to 120. And if I divide both sides by 2, I get y is equal to 60. And remember, this was my packing and unpacking. So if we look back to the graph, we can confirm that the graph was correct. We got 70 and 60, just like we did algebraically. So it's up to you. Whatever's easier, you can solve algebraically or you can solve graphically. And there's also substitution, which we did not go over today. Okay, that concludes our lesson for today. So remember that when you get a total cost, but you have enough information to create an equation with x and y, you can use a system of equations in order to solve and determine what that x value is and that y value.